Our first of three graduate students speaker of the day is Alfredo Delgado. Alfredo Delgado from Ricardo, Texas is currently a third-year Ph.D. student in the interdisciplinary program of molecular and environmental plant sciences who is expected to graduate in December of 2016. He received his bachelor's degree from Texas A&M University in 2010. During this time, he became involved in remote sensing technologies of terrestrial laser, scanning, and ground-penetrating radar. Alfredo went on to complete his master's degree in 2013 in molecular and environmental plant sciences. He also received a certification of both Geographical Information System and remote sensing. Alfredo is now working toward completing his Ph.D. at Texas A&M, in which his primary focus of study is the application and functionality of ground-penetrating radar in agricultural systems. He looks to pursue a career in high-throughput plant phenotyping and phenotyping platform development. Everyone, please join me in welcoming Alfredo Delgado to the stage.
Thank you, Francisco, for the introduction. Howdy, all. Thank you all for being here. I'd like to thank the committee for giving me this opportunity to present my work today. And I look forward to having you guys have a see of what I'm doing here. So I'll be presenting on applications of ground-penetrating radar, a case study for estimating root bulking rate in cassava. So let's dive right into this. There's 15 minutes. So what is ground-penetrating radar? Ground-penetrating radar is a technology that is advanced from archaeology and engineering fields, and we're trying to utilize it in a new perspective. So how does ground-penetrating radar work? In a general sense, ground-penetrating radar works by emitting electromagnetic pulses into the ground, and that signal is transmitted through the ground, and at discontinuities within the ground, reflections or scatters are sent back to the receiving antenna. When that happens, the information is captured as amplitude responses in time of flight. So basically the time it took to get to the position and back, and an amplitude response is given for that position. Here's an example of what's occurring here. Now when that electromagnetic pulse is actually sent into the ground, it's not a single vector as some would imagine, but it's more of a conical shape. So when that conical shape happens, you have differences of distance across space. So what you're seeing here is an example of the antenna starting from position A and ending at a final position. And as it moves across, it creates this hyperbolic function, which doesn't mean that it's getting the outer edge of the object, but more so the distance to the object looking across that conic. So you end up getting that hyperbolic shape, and that's the position of the object. So as we all know in science, we stand on the shoulders of giants. And what I'd like to emphasize here is what's been previously done to get us to where we are now, where the ideas came from. So in this work by Barton et al., the picture on, let's see, your left, we see that frequency is actually a very important measure or for selecting, you got to select frequency very specifically to actually get good information. So why is that? Well, it turns out that high frequencies get better resolution of the objects below ground. So by having high frequencies, we can better delineate differences between object A and object B. But there's a trade-off. The higher the frequency, the faster the dissipation of that energy through the ground. And when that happens, we lose that energy to heat. And that's no longer detectable. So we lose the ability to measure objects further down in the ground. So we need a frequency that can also penetrate and not dissipate. So that was an example of them actually measuring different frequencies for root detection. Now, we know that we can detect roots with proper frequency, but can biomasses be measured? So in the sense of a study by Stover et al., they actually utilized ground-penetrating radar to derive a pixel count method to correlate that back to actual cord weight or cord biomass. So they were able to find a positive relationship going on here. So with that, we moved forward. Let's look at the potential of GPR moving forward. Today we're going to focus primarily on cassava. Cassava is a staple food source for an estimated 800 million people worldwide. And it's actually only third to maize and rice in caloric intake in tropical and subtropical regions. Cassava has actually improved drastically in the past 40 years due to the advancements in breeding of the crop, which hadn't been done previously. As As we advance, though, we come across some issues in traditional breeding, in that the flowering numbers and the seed viability in cassava is very low, so it's very hard to do these large trials. So how can we go ahead and get more information from cassava with less data points, if you will? So we need a way to non-destructively phenotype across different environments at a rapid pace. So with that information, we can then go into what our research question was. Can early bulking in cassava be detected utilizing ground-penetrating radar? So as you can see here, these are examples of 3 varieties of cassava, all at 5-month growth stages. So we can see that the bulking rates are different across those different varieties. Can we detect this utilizing ground-penetrating radar? So how did we go about answering this question? We had a simple trial design where we took 3 varieties of cassava that had differing structures, with 4 planting dates to track the growth over time, with 5 plants per planting date to increase our numbers. Using a ground-penetrating radar system from IDS North America at a 700 megahertz frequency, we then captured 5-centimeter interval data sets in transects. So you'll see how this was broken down later on in the pre-processing steps. Then plants were harvested and weighed for regression analysis. So in the data pre-processing, we had to filter out data because there's a lot of noise that comes back in that signal. There's ringing, there's white noise that comes back in the signal, so that needs to be filtered out. But as you can see in the filtered data, you have these hyperbolic functions that we were talking about as positions of the roots. To centralize that information, we migrate that data to the center. So we basically pull those edges of those hyperbolic functions to the center and create what the new object would be. But you can see these different shades of a dark black and white. What that is that when ground penetrating radar signal returns, it comes back as a positive and negative wave. You have to turn that wave from a negative into a positive to basically give out more of the subtle differences between what's occurring below ground. So we do this Hilbert transformation, which does that for us. It creates an only positive envelope. Once that's done, we then do a maximum likelihood procedure to break this down into classes. Once we have the classes, we know specific positions of cassava that we had measured in the field, and then we know what those amplitudes or those values would have been, and we create a thresholding method. Anything that was greater than that threshold is kept as an object and then counted for pixel counting. So we then decided, let's do a general model. Can a general model be developed for cassava? And what we ended up finding was that we do have a positive analysis, regression analysis of cassava to wet weight. We find that it is increasing, and we tested this to see how significant this was using a bootstrap method in which we did 1,000 iterations of a bootstrap to find out whether or not our R-squared fell within the 95% confidence interval, and we were able to determine that. But we realized that not all cassava varieties respond the same way. So does each variety have a different response? Is there a different equation for each? So we broke this down into variety levels. Here you can see HMC1. We had a moderate relationship in the sense of the R-squared of being 0.54, so we were only able to find about 54% of the variability. There's a topic that we'll discuss later on potentially why this could be the case. But we then again did a bootstrap method to test this and find that our R-squared is significantly found within the 95% confidence interval. Again, so we look now into the second variety, SM1219, and here we have a model that actually has a very high predictive level. And it's proven to be significant. So we'll continue through this. And here's the last one, which is MNGA11. And we find again that this variety has a very good rate, or we find a good positive rate. So what does that mean in the sense of the actual model predictability? So what we did was we held out test data. And within the test data, we applied the model functions to it. And so we have the actual wet weights, the predicted general weights, and the predicted variety level weights. So as you can see that early on within the growth stages, so in wet weights at very low wet weights, we're grossly overestimating the actual amount of biomass. But as we move further on, we can see that starts to normalize as the wet weight increases. So what does this look like when we're actually looking at root bulking, right? So what we want to do is consider root bulking as the change of mass over time, and in this case, a short period of time. So here we're looking from months 3 to 6. We can start seeing these trends occurring of actual bulking. So from month 4 to 5, we see this jump, and what you have here from left to right is your actual wet weight, and then we converted the data to the pixel counts to the general model predicted weights and the variety model predicted weights to see if we can find the same trends. Again, early on, you can see the issue of over-predicting at an earlier growth stage. We look at variety SM1219, and we find a very similar trend, and what we're actually seeing here, and we'll break this down some more, is you can start to see the trend from jump month 4 to 5. This is continuously happening in each of the variety levels. So in MNGA11, we also find the same. This one was more concise in the sense of the actual weights, but we had this high variability within the predicted weights, and that's the estimation issues that were occurring. So when we put this all together, what does this look like in the sense of root bulking rates across variety? When we take this back and we look at only variety level, and we say, can we at least see some kinds of trends of these root bulking rates? We then find that yes, we are following a trend in the sense of changing weights from 4 month to 5 month. This increase is actually occurring. And then you can see in, for instance, something like the second model there, which is of variety SM1219. There's the actual trend is occurring more in month 5 where that increase is happening. So we can potentially say that something is actually occurring at that stage to increase root bulking. But in discussion, some of those issues that we encountered, can that be corrected? Why were we seeing all of this variability? Why were we overestimating at the earlier stages? Well, we're using an equipment that was actually designed for bridge deck work, so it's very smooth surfaces. And the way that the signal works is that pulse is emanated for every 1.34 centimeters using a measuring wheel. As that measuring wheel moves through the ground in a crop field, it sometimes slips and we skip data. So we have to either reset or that data is passed on and we interpolate information from outside. So that's one reason. The other reason is spatial resolution. We know that we have high resolution using 700 megahertz, but that's in the vertical. We're also sampling at 5 centimeter intervals across the X direction and 1.34 centimeters in the Y direction. So we're sampling a very small percentage of the total roots there, if you think about it. Or it could also be a high percentage, but oversampling some of the areas in the sense of the Y direction versus the X direction. Also, signal polarity. Roots are omnidirectional. They change. They're very plastic, right? So when we use this antenna, what's happening is that when the information is returned, it's very sensitive to objects that are perpendicular to the antenna. But if the object isn't perpendicular, that response isn't really coming back as intense. Therefore, the value of the amplitude response is much less. So when we do this thresholding method, we then lose some of that information because we're actually throwing it out as not pertinent data. And when in reality, it could have actually been a root. So is the thresholding method really the best method, or should we go about some other approach? Also, soil conditions. With varying soil conditions, you change the parameter of the signal. As a signal moves through soils, that's very dependent on the soil type. So for instance, in a sandy soil, the signal can move very rapidly, the signal is very clean, and there's not much disturbance. Whereas in clay soils, that signal is dissipated really fast in heat, and we lose a lot of information as we move through that soil. So HMC1, the variety that had a very low relationship, was actually planted in a clay soil, which was a wet clay soil, and that could have been one of the reasons for having such poor information returned. So another issue is objects in soil. Again, we're looking at anything that's below ground. Any discontinuity that's being reflected back is being captured. So if that's the case, then are we overestimating because of that? In that case, is there a way to go ahead and discriminate between what's occurring in the ground? So maybe using frequency filtering methods and whatnot can help reduce that error. So, and then plant development. Root architecture is vastly different across different cassava varieties. And based on that architecture, how does that signal respond to that? Again, the polarity of the signal is very dependent on the root position. So if the root is very vertical, then we no longer have that perpendicular response. We now have to do a cross analysis where the signal goes from one side to the other and intercepts in that perpendicular manner. So we weren't using an antenna that did this, so we may also be losing information there. So although we were able to find some relationship, there are still some issues that need to be looked at. And with that, I'll wrap up there and like to acknowledge the U.S. Barlog Fellows in Global Food Security for giving me the opportunity to visit CIOT and capture this data. So CIOT, the Center for International Agriculture in the Tropics, and IDS North America are a collaborating partner with the antenna systems. So thank you, and any questions?
Thank you, Alfredo, for your presentation. We have a few minutes for questions. If anybody has a question, raise their hand. The volunteer will walk over you. We have a question over there. And if via the webinar, please submit your questions to the webinar text box if there's any questions.
Yes, I have a question on using this on potatoes. If you think that it would work better or worse or maybe the same.
Right. So with potatoes, the issue is that the antenna is based on ground contact. You have to have a solid contact to the ground. There can't be an air pocket between, or you get a high reflection at the first impact and you lose a lot of the information. So with potatoes being more leafy shrub-like versus a single stem or you know, more erect stems, then that ground contact is a little more difficult. So you need to use a different antenna array system in the sense of maybe airborne antennas where you can have elevated antennas, or antennas that actually go crosstalk. So one from the left talking to one on the right. So it's moving across the soil versus down into the soil so that you can get around that issue. So there's potential, yes, depending on which technology you use.
Thank you.
Thank you. We had one more question, was there? Is there any other questions? All right. Thank you very much, Alfredo. Let's thank him again for his wonderful presentation.